Yo, what's up, Sci-Fam? It's your boy Nickel, and today we're going to talk about Newton's first law of motion. So let's add that title to the page up there at the top, Newton's first law of motion, and then we're going to look at two different situations and how they kind of relate to each other. We'll reframe Newton's first law of motion into a new way to look at it, and we'll define inertia as well and have a couple examples at the bottom. So you can see how you need to structure your page, and let's get started learning about Newton's first law of motion. So Newton observed that an object that's at rest tends to remain at rest. Think about this. There's a big boulder and it's just chilling there. Well, if you come back in like 30 years, that boulder's probably still chilling there. He also noticed that an object that's in motion tends to remain in motion. So if you think about this, if you were to kick a soccer ball, that soccer ball just keeps on rolling along and rolling along and rolling along. Unless, yep, that's right, because it doesn't go on forever, does it? You all know that. You've probably witnessed that. Unless that object, whether it's the boulder or the soccer ball, is acted upon, so some type of action, if the object is acted upon by an outside force. Now, what do I mean by an outside force? Well, this soccer ball is going to continue moving until it hits a wall, or until the grass causes enough friction to cause it to stop, or until somebody that's playing soccer comes in and kicks the soccer ball, and then the soccer ball changes direction. Now the boulder is going to stay there unless maybe there's a torrential downpour and there's a bunch of rain, and the rain floods underneath the boulder and it causes the boulder to start moving down the hill. So an object at rest will remain at rest, and an object in motion tends to remain in motion unless it is acted upon by an outside force. Something else comes in to get it moving, or to stop its motion, or to change its motion. All right, so Newton's first law of motion could also be described, and sometimes it is described actually, as something a little bit different, with a new vocabulary term, and it's described as the law of inertia. It's kind of an easy way to describe Newton's first law, but the only way that we can use this definition or use this reframing of Newton's first law of motion is if we understand what the word and what the concept inertia actually means. So let's define what inertia is. First off, it's a really cool word, inertia. Inertia is the amount. So it's like a value. It's a way to quantify something, have like a number behind it. Even though we don't typically have a number, we can compare it from one thing to another. So it's the amount, it's how much of resistance. The amount of resistance an object has to either stop, for stopping its motion if it's in motion, or maybe even starting its motion if it's not in motion, or if it's in motion, maybe you're not going to stop it, but you want to change its direction. So you're going to be changing the motion. So inertia is the amount of resistance, how hard it is to stop something's motion, to start its motion, or to change its motion. So inertia. Okay, well, let's look at first. Let me get a good color here for drawing an elefante. All right, so to draw my elephant here, I'm going to give it an ear, go down for the trunk, give it another ear. We'll even let it have a nose so we can see. There's its trunk, and then, yeah, its body is not as good. Well, that's okay though. Yay. Okay, this is my elephant. And if we think about an elephant versus, let's say, a mouse here, give it a nose with some whiskers, and some ears, an eye, and a tail. Ooh, that's a bad tail. Let me try that again. Okay, so if we look at these two objects, there is much more mass in an elephant. That is for sure. So therefore, if you have more mass, then you end up with more inertia. So let's write more mass, more inertia. So imagine, to try to pull that elephant, if it was just standing there, it would be really hard because it's so heavy. Imagine if it was in motion. It would be really hard to stop it because it's so heavy. If we have less mass, like a mouse, then we end up with less inertia. Because if you think about a mouse, it'd be really easy for us to go and pick or drag a mouse across the floor. And if it was running across the floor and it ran into our foot, we might just barely notice that it actually ran into our foot. So if you have more mass equals more inertia. Less mass equals less inertia. All right, let's take another look at another example. In this example, let's draw the Titanic. Let me get a better color here for the Titanic. Let's go with this color here. So I'm just going to draw a boat, and it had like this platform here, and it had these like 4 big smokestacks. 1, 2, 3, 4. It had tons of rooms for people to be in here. There was a huge boat. Okay, and we could compare this maybe to like a wave runner. Let's draw a wave runner here, maybe something like that. Okay, so if we look at these two items, here we have more mass. Here we have less mass. So which one has more inertia? Which one is going to be harder to actually turn if it was in the water? Whoa. All right, more mass means we have more inertia, which means we have more resistance. Okay, inertia is the amount of resistance something has. So if we have more mass, we have more inertia, more resistance to move that boat. If we have less mass, then we end up with less inertia, and it's easier. There's less resistance. So there's inertia. Less mass, less inertia. Now, if we think about this in reality, actually, which is kind of crazy to think about, but the Titanic, the reason it sank is because it hit an iceberg. Well, guess what? They actually saw the iceberg and they tried to change the direction of the boat. So let's say that this was the iceberg here and the boat was heading towards the iceberg. Well, they're like, oh no, there's an iceberg ahead, move the boat. And so they actually turned the rudder on the boat and the boat started to turn. But it had so much inertia that it takes a lot of effort to get the boat to turn. They couldn't just turn the boat really sharp because it was already in motion on the water. So therefore, even though they saw that the iceberg was coming, they were unable to move it quick enough, and it ended up still hitting the iceberg because it had so much inertia. Now, if that was a wave runner and it saw that iceberg, it could have just done a 180 almost because it has so little inertia that it's easy to move that boat, to move that wave runner. All right, let's do another example here. This one is going to be, we're going to look at speed, or how much motion something has. Okay, so I'm going to show 0 on here, and we'll show 100, and then we'll say 50 is in the middle. So we're at 50, 0, and 100. So if I were to draw a line in here to show that at first we're going to have low speed, and then later we're going to have faster speed. So what we find is if we have the same object, so let's imagine that we have, let's go with a baseball. Okay, so let's draw a baseball here, and let's imagine that this baseball is going to be traveling. At first, it's traveling, I don't know, maybe 30 miles an hour, and then it's traveling 80 miles an hour. Well, if you wanted to change the direction of that baseball, or if you want to stop the baseball's motion, or if it hit you and it then stopped its motion, well, we would be able to definitely feel its inertia, how much resistance it has to stop. So imagine this baseball's flying at you at 30 miles versus 70 miles. So if we have less speed, then we have less inertia. And if we have more speed, it's the same object, but just going faster, then we end up with more inertia. This is why baseball pitchers like to throw their fastball as fast as possible, because the more speed they put on it, the harder it is, the more resistance it has for that batter to actually change the motion of that baseball. More inertia, more resistance. Less inertia, less resistance. So let's take a look at some examples here. Here's our person who has less inertia running into something with more inertia. Even though the person has less inertia, they still impact the elephant. Watch the elephant. It moves a little bit, but hardly at all. Yet the person with less inertia falls to the ground. You can see the resistance to them moving. If you have less inertia, it's way easier. You have less resistance to move, so you fall to the ground. The elephant has more inertia, so has more resistance. It doesn't fall to the ground. Now, inertia is also the reason why you should wear your seatbelt. Because if you're not connected to the car, remember, an object in motion will remain in motion. So if you're sitting there with the car and the car's pushing you forward, but then the car stops, your body won't stop because you're not connected to the car. So you will remain in motion, and you will go ahead and take a mouthful of the dashboard if you don't have a seatbelt on. Now you can see it a little less dramatically with the giraffe's neck. The giraffe's neck continues moving forward because it was in motion, and nothing stopped the giraffe's neck, so the giraffe's neck remains in motion. Remember, Newton's first law of motion is the law of inertia. An object in motion will remain in motion, like the person or the giraffe's neck, unless it's acted upon by an outside force. The dashboard was the outside force that stopped the person's motion. Not very comfortable. Wear your seatbelt. Okay, also, an object in motion will remain in motion. So, if this hamster is running in the wheel and then it just stops its motion, well, the wheel is still moving, so it will get caught up and it will continue to go with the wheel. The wheel doesn't just automatically stop. We'd have to have something that stops the wheel's motion. The person is running, they jump up. Even though they jump up, they don't just go straight up. They were moving forward when they jumped up, so then they continue their forward motion. That's why you move forward, because of Newton's first law of motion. You're running so fast, that means the faster you run and then you jump, that means the further you're going to go, because you were in motion. You jump, you continue to go in motion forward. Now, this is a great example here with the water balloon. So, if we think about there being water in there, the water is being held by the water balloon plastic, or the latex there. So when the latex is no longer there, an object at rest wants to stay at rest. So we'll actually see the water just float there for a second until gravity impacts it and it starts to then fall towards the earth, or get attracted down towards the earth. And it's in motion until it hits the top of the guy's head. So all the water around his head continues in motion. The water that hits his head found a resistance and it stops moving. An object at rest will remain at rest unless acted upon by an outside force. This time it's gravity. This time, the same thing happens. These leaves are at rest and they're not connected to the cushion below it. So when the person goes through the leaves and hits the cushion, the leaves stay there because they're not connected. They're going to stay at rest until they're acted upon by an outside force. Oh, gravity is the outside force, and then they go down. So you can see inertia keeps those leaves there, and then gravity is what causes them to move once they move. That one's really cool. I like that one a lot. Inertia. Okay, well, guess what? Same thing here. If you've ever seen this trick done by a magician where they have a bunch of stuff on the table, then they grab the tablecloth and they yank the tablecloth and the stuff stays there. Because if we think about a free body diagram, this car has the downward force of its weight and there's the upward force of the truck bed. But when that truck bed is no longer there, then there's just a downward force of the car, and so the car doesn't move forward because it's not attached to the truck bed. So it just goes straight down. And here, an object in motion will remain in motion. So an object in motion will remain in motion. So those wheels keep on moving because they were in motion. So when they fall off the car, they go at the same speed that they were going when they were on the car until they hit an outside force, which in this case is the wall. So they don't just stop where they fell off. They keep moving because they were in motion. And that's why if you're ever in a car and you throw a ball up in the car while you're in motion, that ball stays there with you because it's moving with you down the road. And so when you throw it, it's actually moving forward. Just like the spit of the llama. Is that if it spits straight up, it has that forward motion with it, and so it would land right on top of the llama's head. So here is Newton's first law of motion in action. Now you know why you got to wear a seatbelt, and why when you throw something up in a car, if you're in the front seat, it doesn't fly to the back seat, it stays right there with you because of Newton's first